Myself, Dr. Prabir Panja, from Department of Applied Science, Huldi Institute of Technology. Today, we'll discussing about um, the nullity, rank, and other properties of the linear transformation. Now, suppose you have these things: nullity. Suppose we have these things: nullity of T, nullity of T. So let T be a linear transformation from V to W. Okay. Suppose T be a linear transformation from V to W. So V and W are the vector spaces. Then first of all, we'll compute kernel of T. Kernel of T. Kernel of T is what? Kernel of T is a set of vectors alpha belongs to V. Okay, whose images under the transformation T is null. Okay, so that collection is kernel T. Now, if we take the dimension of kernel T, then that will gives us the nullity of nullity of Okay, so if we want to compute the nullity of any linear transformation, first we have to compute kernel T, then dimension of kernel T will gives you the nullity of the transformation T. So let us take an example. Find find the nullity nullity uh, of the linear transformation uh, T from R2 to R2 defined by uh, T of x1 comma x2 equal to T of x1 equal to x1 plus x2 comma x1 minus x2. So this is a linear transformation defined here, and we have to compute the nullity of this linear transformation. Now, first of all, we will compute the kernel T. Um, so first, we'll take let T of x1 comma x2 equal to 0 0. So it will gives us x1 plus x2 comma x1 minus x2, that is equal to 0 0. So it will gives you x1 plus x2 equal to 0 and x1 minus x2 equal to 0. So if we solve these two, ultimately after solving it, the solutions will be x1 equal to 0, x2 equal to 0. So the kernel T set uh, will element 0 0. Okay, and 0 is 0 is not a linearly independent vector, so that's why dimension of kernel T become 0. So dimension of kernel T is nullity, so that's why nullity uh, T is equal to 0 for this linear transformation. Okay, next we'll go for a rank of a linear transformation. So let us take one linear transformation T from V to W. Okay, let us take one linear transformation T from V to W. Then and then we'll take T of V. T of V, that is the that is called the image set of the mapping key. Okay, then then we know that we know that uh, TV is a subspace of W. Okay, and then the of dimension of TV is called the rank of the linear transformation T. Okay, so if we want to compute the rank of any linear transformation T, first of all we have to compute the TV, that is the image set, and in the image set we have to compute the basis of the image set, and from the basis of the image set we can easily find out the dimension of the image set, that is the rank of the linear transformation. Let us take one example here. So, uh, let's find find the rank of the linear transformation of the linear transformation rank of the linear transformation T from R4 to R2, defined by uh, T of x1, x2, x3, x4 is equal to 3x1 minus 2x2 minus x3 minus x4, comma x1 plus x2 minus 2x3 minus 3x4. Okay, so we'll try to find out the rank of the linear transformation given here. Let us see how we can do this. So first of all, we'll write the mapping the transformation here. uh, T of x1, x2, x3, x4 is equal to 3x1 minus 2x2 minus x3 minus x4, comma x1 plus x2 minus 2x3 minus 3x4. So uh, first of all, we'll try to find out which vectors will generate all the images of the linear transformation. So if we take common x1 from here, we'll get 3 comma 1, and x2 it will be minus 2 comma 1, plus x3 it will be minus 1 comma minus 2, plus x4 it is minus 1 comma minus 3. So we can see that these four vectors, uh, 3 1 3 1 minus 2 1 minus 1 minus 2 and minus 1 minus 3 will generate the basic the image set of T. Okay, now we have to find out how many of them are linearly independent. Okay, so to check the linearly independency of the vectors, we'll take the help of uh, elementary row operation of the matrix. So first of all, we'll take all the vectors in within a matrix. So this will be 3 1 minus 2 1 minus 1 minus 2 and minus 1 minus 3. Four vectors, and we'll apply elementary row operation to check which are the linearly independent vectors. So first of all, we'll interchange R1 and R4. Interchange these two row of the matrix. So it will be minus 1 minus 3 minus 2 1 minus 1 minus 2, then 3 1. Okay, now if we take another operation here, uh, if we take R2 minus 2R1, uh, R3 minus R1, R4 plus 3R1. If we apply elementary row operation over this last updated matrix, it will become minus 1 minus 3, then 0, R2 minus 2 R1, so this will be 0, and minus 1 plus 6, sorry, plus 1 plus 6, it will be 0 7, R3 minus R1, so it will be 0, it is 1, then R4 plus 3 R1, so this will be 0, R4 plus 3 into R1, so 1 minus 9, it will be minus 8. Okay, so again, if we apply another operation here, mm, if we apply R4 plus 8 into R3, then it will gives us minus 1 minus 3 0 7 0 1 uh, 0 0. So after that, if we take another operation, it will, let us take R2 minus, sorry, R2 minus 7 into R3. So this will gives you minus 1 minus 3 uh, 0 0. Okay, 0 1 0 0. Okay, so after that, we can apply several many elementary row operation, but we can't make a row completely 0, so that's why we can stop here. Now here you can see all the dependent vectors becoming 0, and independent vectors remains non-zero. So here we can say the independent vectors are independent vectors among the four vectors are among the four vectors uh, are, one is minus 1 minus 3, another is uh, minus 1 minus 2, minus 1 minus 2. Okay, except that except this, all the dependent vectors becoming 0. So the dimension, so the dimension of the image set, that is equal to dimension of TV becoming, or we can say the rank of the transformation T is equal to. So in this way, we can compute the rank for uh, any linear transformation. Now we'll go for important theorem, that is called the Sylvester's law. Sylvester's law. So suppose if we have linear transformation T from V to W, where V and W are the vector spaces, then where V and W are the vector spaces over the field F, then rank T plus nullity T, that will be equal to dimension of V. So if using this Sylvester law, if rank T is known, we can find out nullity T, or if nullity T is known, we can find out uh, rank T very easily. Okay. Now we'll compute the matrix representation of the linear transformation. Matrix representation of the linear transformation linear transformation. We can write the linear transformation T in terms of matrix. Suppose we have a linear transformation T from P to W. Okay. So matrix representation will be always with respect to some basis of the two vector spaces. Suppose the basis for V is V1, V2 dot Vn. Okay, and the basis for V. Similarly, if the basis of W is W1, W2 dot W1. So this is the basis of W. Okay. Now what we'll do, first of all, we'll compute T of V1. Okay. So suppose this value under this transformation T becoming V1 star, then we have to try to write this V1 star as a linear combination of W1 to W. That is the basis of W. So we will try to write V1 star is C11 at W1 plus C12 W2 plus dot C1 and Wn. Similarly, we will compute T of V2, that will be V2 star. Again, we will try to write T C21 into W1 plus C22 W2 plus C2 NW. In this way, uh, we'll take the value of T of Vn. So suppose the value under this transformation is Vn star, so we'll try to write it as Cn1 W1 Cn2 W2 plus Cnn W. Okay. Now using this n number of equations, we'll find out the matrix T with respect to the basis of P and W. So here all the terms C11, C12 up to C1n all are constant. So we'll write this constant column wise: C11, C12 dot C1n. Similarly, from the second equation, we will take all the constants C21, C22, C2n, and we will write it column wise. So this will be C21, C22 dot C2n. In this way, we can go to the nth equation, and in the nth equations, constants are Cn1, Cn2, and Cnn. So we'll write here Cn1, Cn2 dot Cnn. and ultimately this will gives the matrix representation of the linear transformation T. So this is the way to get it. Now suppose we have a particular problem. uh, Suppose we have to compute uh, the mapping, the matrix for the mapping T. uh, that T is a transformation from V to W defined by P of fx is equal to f dash x. Okay, and where V V is the set of, and V is the vector space of all polynomials of degree less equal to 2. Mm, Sorry, less equal to, it will be 3, less equal to 3, and W is the vector space vector space of all polynomial nomial of degree uh, less equal to. The question is find the matrix representation of T. Matrix representation of the transformation T. So T is a linear transformation defined this way: T of fx is f dash x, and V and W are the two vector spaces. V is the collection of all polynomials degree less equal to 3, and W is the vector space of all polynomials of degree less equal to 2. Now, using these two values, will compute the matrix representation. So, first of all, we have to compute the basis vectors for V. Now, the basis set of V are, since V is the vector space of all real polynomial of degree less equal to 3, so its basis set must contain this vector 1 x x square and x cube, because with the help of this 1x x square x cube we can construct any 3-degree polynomial. And similarly we can find out the basis set of W, and the basis of the set of W contains this type of vectors 1 x square, because W is the collection of all polynomials of degree less equal to 2. Now, as per our theoretical concept, first of all, T of fx is defined this way: f dash x. So first we'll take T of 1. That one will come from the basis set of V. That is the first element from the basis set of V. It is 1. Next, so T of 1, it will be 0, because the derivative of 1 will be 0, and we have to write this one as a linear combination of the basis set of W. So this will be 0 into 1 plus 0 into x plus 0 into x square. Similarly, if we take the second element from the basis set of V, it is x. So T of x, that will be uh, 1. After derivatives, x become 1. So we have to write this 1 as a linear combination of 1 x square. So we can write it as 1 into 1 plus 0 into x plus 0 into x square. Similarly, if we take the third element from the basis set of D, it will be 2x. So we have to write again 2x as a linear combination of 1x x square. So this will be 0 into 1 plus 2 into x plus 0 into x square. Similarly, if we take the last element from the basis of the basis set of V, it will be 3x square. So it will be 0 into 1 plus 0 into x plus 3 into x square. Now, with the help of this fourth equation, now we'll write the matrix representation for the transformation T. Transformation T. Now, for this, first we have to collect all the constant from the first equation, and we have to write all this in column wise. Now, from the second equation, we have to collect all the constants. So it is 1, 0, 0. Now from the third equation, we will collect all the constants. So it will be 0 to 0. Again from the fourth equation, we will take all the constants. So it will be 0, 0, 3. So ultimately, we can get the matrix representation for the linear transformation T. So this is the way to find out the matrix representation for any linear transformation T. Okay. Now let us take another example how to find out the matrix representation of a linear transformation. So let us take an example. Determine the matrix for the linear transformation for the linear transformation linear transformation at T from R5 uh, to R3 defined by defined by defined by T of x1 x2 sorry x1 x2 x3 x4 uh, sorry T of x1 x2 x3 x4 x5 equal to x2 x3 x4. Okay, so with respect to the standard basis of R5 and I3, now we'll compute the matrix representation for the linear transformation T. So first of all, we have to take the uh, standard basis for R5. For R5 is standard basis for R5. It will be 1, 0, 0, 0. If no bases are mentioned in the question, always we have to take the standard basis for the vector space V and W. So here V is R5 and W is R3. So that's why first we'll take the standard basis for R5. Is next is 0, 1, 0, 0, 0. Next element is 0, 0, 1, 0, 0. Then next element is 0, 0, 1, 0. Then last element is 0, 0, 0, 0, 1. So this is the standard basis for R5. Now we'll take the standard basis for R3. The standard basis for R3 is um, 1 0 0, next 0 1 0, then 0 0 1. Now with respect to the these two bases, I'll compute the matrix representation. First of all, our mapping was this T of x1 x2 x3 x4 x5. That value is equal to x2 x3 x4 x2 x3 x4. Okay, so if we take the first element from the basis of R5, it will be T of 1 0 0 0. So its image under this transformation will be 0 0 0. Again, you have to write this 0 0 0 as a linear combination of the standard basis of R3. So it will be equal to 0 into 1 0 0 plus 0 into 0 1 0 plus 0 into 0 0. Now we'll take the next element from the basis set of R5. So it will be 0 1 0 0 0. Now under this transformation, its image will be 1 0 0. Again, we have to write this 1 0 0 as a linear combination of the basis set vectors of R3. So this will be 1 into 1 0 0 plus 0 into 0 1 0 plus 0 into 0 0 1. Okay. Now if we take the third element from the basis set of R5, it will be 0 0 1 0 0. So its image will be 0 1 0. Again, we'll write it as a linear combination of the vectors of R3. So it will be 0 into 1 0 0 1 0 0 plus 1 into 0 1 0 plus 0 into 0 0 1. It will be 0 0 then 1 0 0 1. Now if we take the fourth element 0 0 0 1 0, so its image will be 0 0 1 0 0 1 under this transformation. So if we write this element as a linear combination of the uh, vectors of R3, it will be 0 into 1 0 0 plus 0 into 0 1 0 plus 1 into 0 0. Now we'll take the last element from the basis of R5, that is 0 0 0 0 1. So under this transformation, its image will be 0 0 0. Now we can write it 0 into 1 0 0 plus 0 into 0 1 0 plus 0 into 0 0 1. Now we have a total 5 equation, from this five equation, we can write the matrix representation for the linear transformation. So if we see the uh, first equation, then in the first equation the constants are only here 0 0 0, and we'll write it column wise. So it will be 0 0 0 from the first equation. From the second equation, the constants are 1 0 0. Again, if we write within the matrix, it will be 1 0 0. From the third equation, if we see the constants, it is 0 1 0. So this will be 0 1 0. And from the fourth equation, the constants are here 0 0 1. So it is 0 0 1, and the fifth equation it is 0 0 0. So this will be 0 0 0. So this is the matrix representation for the linear transformation T from 5 dimension to 3 dimension. Okay, so this is the end of today's class. Okay, thank you.